Many terms in statistics are used interchangeably, yet they possess distinct meanings. Two such terms, often confused, are probability and likelihood. While both deal with the chances of events, understanding their precise definitions is crucial for accurate statistical reasoning. This video will clarify the fundamental difference between them. Probability is a measure of the chance that a certain event will occur. It quantifies the uncertainty of an outcome given a specific process or set of parameters. Think of it as a predictive tool. We know the characteristics of a system, and we want to predict what might happen. More formally, probability is defined over events within a sample space. If an experiment can produce n equally likely outcomes, and an event A occurs in m of these outcomes, then the probability of event A is given by m over n. This implies that the underlying process generating the data is known. Consider a fair six-sided die. We know each face has an equal chance of landing up. The probability of rolling a 3 is 1 over 6. Here, the parameter, which is the fairness of the die, is assumed to be known. We are predicting an outcome based on this known parameter. The probability of an event A is typically denoted as PA. When we want to explicitly state the probability of observing specific data x given a known parameter theta, we write P, x, theta. This reads as the probability of x, given theta. Likelihood, on the other hand, approaches the problem from the opposite direction. Instead of predicting an outcome from known parameters, likelihood helps us infer the parameters of a model given observed data. It's an inferential tool, working backwards from observations. The likelihood of a parameter value theta, given observed data x, is proportional to the probability of observing x if theta were the true parameter value. It is not a probability distribution over the parameters. Rather, it's a function of the parameter theta for fixed data x. Here lies the core distinction. Probability is a function of the event, given a fixed parameter. We ask, what is the probability of this data, given these parameters? Likelihood is a function of the parameter, given fixed data. We ask, what are the most likely parameters, given this observed data? Imagine you flip a coin 10 times and observe 7 heads. You don't know if the coin is fair. The likelihood of the coin's bias, say P, given 7 heads and 10 flips, allows us to estimate P. We are trying to find the P that makes observing 7 heads most likely. The likelihood function is commonly denoted as L, theta, x. This is read as the likelihood of parameter theta, given the observed data x. Notice its structure is very similar to the probability notation, p, x, theta, which is often the source of confusion. Despite their distinct roles, probability and likelihood are intrinsically linked. The likelihood function is often numerically equal to the probability of the observed data under a specific parameter value. However, their interpretations, especially regarding what is fixed and what is varied, are fundamentally different. We use probability when we have a model with known parameters and we want to predict future observations or understand the chances of certain events. For instance, calculating the probability of a specific hand in poker, or the chance of rain tomorrow based on meteorological models. Likelihood is central to statistical inference, particularly in maximum likelihood estimation. It allows us to estimate unknown parameters of a population from a sample of data. For example, estimating the average height of a population, or determining the effectiveness of a new drug based on trial results. Confusing probability with likelihood can lead to misinterpretations in statistical analyses. Treating likelihood as a probability distribution over parameters, for example, is a common error that can affect conclusions drawn from data. Understanding the direction of inference is key. In summary, probability quantifies the chance of data given known parameters, moving from model to observation. Likelihood evaluates the plausibility of parameters given observed data, moving from observation back to the model. Recognizing this critical difference empowers more precise and robust statistical understanding.